Good morning, everybody. How are we feeling? Good? Yeah! Nice. Nice. If you think you feel like crap now, wait until tomorrow. So a quick programming note. We know we absolutely heard about all the problems in the hallways yesterday, and you noticed we made a couple small changes yesterday that I think seem to improve some things. We made another kind of substantial change today. So what we did was DEF CON 101, that has moved to Bally's Gold, so over at the other part of the hotel. Track 4 moved to where 101 was, and then if we do need to corral all of you fine folks, we will probably be doing it in the area where Track 4 used to be. Make sense? Cool? So hopefully that will make the congestion problems a lot better today. But that said, hey, keep cooperating. You guys were great yesterday, especially for some of the big talks like the Tesla talk, and I'm sure we're going to have some talks that are just jammed in here. So keep playing along, and we'll all have a good time, right? But hey, let's talk about Macs. How many people in here have Macintoshes? Yeah, it's nice hardware. It's nice hardware. And you know, depending on who you ask, some people may have a nice sense of oh, I'm so safe because I have a Macintosh, that kind of thing. Well, we're going to learn, once again, why that kind of idea is false, and we're also going to reinforce the rule of, and say this one with me, physical access is total access. No? All right. It's early still, I guess. All right. Well, let's give our guys a big hand.
Thank you. So good morning. As our goon alluded to, we're going to be talking about MacBook physical security, but also some software security. So I'm Trammell Hudson, and I really like to take things apart. I've been doing a lot of work in reverse engineering, things like the camera firmware for Canon SLRs, and I've produced a GPL'd runtime to let folks write their own programs to run on it. I also really enjoy digging through old ROMs, looking for Easter eggs, such as the Apple team that built the Mac SE that they hid in their ROMs back in the 1980s. And this project got started a couple of years ago when my employer, Two Sigma Investments, a high-tech hedge fund in New York City, wanted to deploy MacBooks. And there had been some reports about rootkits, and I was asked to use my reverse engineering skills to look into if it's possible to defend against them. Because we have a lot of concern about security, both physical and software.
Hi, and I'm Zeno Kova. Corey Kallenberg couldn't be with us this year at the cons. But this past January, Corey and I started Legwood Core, and we're basically the only company that's focused specifically on PC firmware security. So firmware for x86 PCs, Macs, and then all the peripherals as well. All the hard drive firmware, NIC card firmware, GPU firmware, all that other stuff that people talk about at conferences, but nobody ever seems to get around to actually checking. That's what we do.
So this talk sort of got its start last year at CCC in Hamburg. I presented ThunderStrike, which I suppose we can now call ThunderStrike 1, which was the first firmware rootkit for MacBooks that we learned how to, what protections Apple had on their firmware and how we could generate files to write into the ROM. The day before my talk, Rafal and Corey presented some really amazing attacks on UEFI security, including one called Darth Venomous that I found very interesting and really wanted to see if it was possible to port it to the Mac. So we teamed up, and what we found is that, yes, it is possible to port vulnerabilities from Windows systems to Macintoshes and other systems. And that's the key message of this talk is that these most EFI vulnerabilities, many EFI vulnerabilities, are OS independent. They're in a lot of cases hardware agnostic, and that vendors and everyone needs to be aware of that. So that's enough talk. Let's jump straight to the demo. So ThunderStrike 2 is an improvement over the original ThunderStrike in that now physical access is no longer required to initiate the infection. That it's possible to, with remote code execution that can then use whatever root exploit of the day to escalate to root. Once at root, it can install the whitelisted direct hardware kernel extension, which allows it to map all of physical memory, including the memory mapped SPI flash registers. On some machines, on some MacBooks, it's able to immediately unlock the flash and start writing into it. And this is using the information, again, from the ThunderStrike 1 talk about how are the firmware volumes organized, how are they integrity checked. So in this case, we've added we've appended a payload into the free space, and we've updated the CRC. While we are scanning memory, we also go ahead and walk the PCIe bus, looking for devices with option ROMs. And we're able to write the payload into those as well. In this case, much like ThunderStrike 1, we're using the gigabit Ethernet adapter as a payload transmission vector. So the option ROM now contains the payload, and the MacBook also has written the payload to the motherboard boot flash. When we reboot the machine, we will see the ThunderStrike logo come up. We are deliberately not trying to be stealthy with the proof of concept. So there's our awesome ASCII art logo hidden in the boot ROM. And this is controlling the system from the very first instruction that it executes. The viral transmission means that we can put that laptop aside and share the adapter with another one, which is pretty common in a lot of corporate environments. So now the EFI firmware loads the exploit from the option ROM, and it's not able, on this MacBook, it's not able to unlock the flash immediately. But what it can do is use the Darth Venomous attack that was presented at CCC by Corey and Rafal to hook the S3 resume boot script. So then when the kernel boots normally, and then at some point later, the system goes to sleep, either via software or just the user closes it. And the vulnerability is that when the CPU enters the low power state, all of the flash protection bits get reset. So when the system wakes back up, the S3 script, which is executed upon resume, that we have injected code into, writes ThunderStrike into the motherboard boot ROM. And this is not on the hard drive, so you reinstall OS X and it doesn't fix it. You swap out the hard drive, it doesn't fix it. And possibly even you swap to a new computer, you could reinfect through the peripherals that you retain. So at this point, as I mentioned, we're not stealthy. So when the system reboots, we'll see the logo. A weaponized version could use SMM or virtualization, similar to the Blue Pill attack from a few years ago, to really do a good job of hiding from attempts to detect it. So this laptop's now infected, and the other part of the infection that's new is that it's watching for clean Thunderbolt adapters to be plugged in, and then it writes the exploit into those adapters so that they can then continue to spread to other machines, possibly crossing air-gap security perimeters. So what we've demonstrated with this proof of concept is a somewhat unique life cycle for a firmware worm that starts with a software exploit, is able to write itself into the boot flash on the motherboard. They can then infect Thunderbolt and other removable option ROMs, which are able to hook the S3 resume script and then write themselves into the boot flash of other machines and continue the infection.
Right, so that's the black magic attack here, but now let's get into understanding how it works, right? So the key point again is that firmware vulnerability is found across many systems. When we've disclosed things in the past, they would affect many different PCs, and here we're showing they affect Macs as well. A little quick background on the transition of firmware on modern systems, right? So you'll hear us often use the term BIOS interchangeably with EFI or UEFI. When we say BIOS, we just mean generically firmware, but firmware for x86 PCs typically. So Intel started the EFI Extensible Firmware Interface project back in the late 90s to replace BIOS. So they were trying to create a non-backwards compatible IA64 architecture. They said, we want to get rid of all this legacy cruft. We don't want to keep working on this, thing from the 80s. And so they said, okay, for our new architecture, we're going to have a new modular, well-designed version of the firmware. So they did that. They did that on their Itanium systems. And then when Apple first moved from PowerPC chips over to Intel chips back in the early 2000s, they said, okay, we'll go ahead and use this new type of firmware that Intel recommends. That was the Intel EFI 1. Whatever version. So in 2005, Intel was trying to bring more people in the fold, get wider industry adoption. So they created the UEFI forum as a sort of industry consortium to collect up many more players, get all of their buy-in, get all of their contributions, and get them to actually start using this. So the original EFI 1.1 was deprecated, and now everybody was talking about UEFI and the EDK development kit, the EFI development kit. So, of course, when they got more industry buy-in, they didn't just go ahead and rewrite everything from scratch, right? It just meant they continue to evolve with more people's input. So Apple forked it back at the 1.1, and you would expect Apple's implementation to generally diverge from the rest of the world and the rest of the UEFI implementations. But still, there's, of course, going to be millions of lines of code that are similar from the old stuff and the new stuff. The way that the whole UEFI ecosystem typically works is that there's a single open source reference implementation. That's the EDK2, the EFI Developers Kit 2. Single reference implementation, which is then modified by the independent BIOS vendors like AMI, Phoenix, and Inside. They go ahead and add value to the systems, right? They have to compete amongst each other in order to say what new features they've added that the other guys haven't added, and that's how they're going to get OEMs to buy theirs. And then the OEMs buy and maybe manipulate if they've got enough BIOS if they've got enough BIOS engineers themselves. The OEMs will do further customizations on this, and then that's what we ultimately see. But because of this hierarchical nature, that means fixes that happen, the open source reference implementation, take a long time to trickle down, right? Months and potentially years. And so a big point of this talk is to be, look, no one's a unique and beautiful snowflake. Everybody looks the same. So we took a ASUS machine that we did with our CanSec West talk. We did an analysis. We showed here's all of these places where an attacker could hook all of the systems that are out there today. And we took that, we analyzed it, and so its control flow graph picture is a little bigger because it's got comments in it. But then you take a ASUS desktop and you take a MacBook Air, Ultrabook if you will, and the thing is, they look all the same, right? Their control flow graphs look the same. They call the same functions in the same order. There has to be some level of similarity in order for EFI or UEFI systems to implement that extensible firmware interface, right? There's a spec out there that says how the firmware interface works, and to conform to that, you have to look the same. So, call the same functions in the same order, have the same assembly in the same order. No one's system firmware, if they're EFI derived, is unique and beautiful snowflake. So that means that there's going to be shared vulnerabilities. All of the stuff that we've been disclosing over the past couple of years for PCs, does it affect Macs? Well, spoiler alert, yes. Right? So this means that there's all these vulnerabilities which are out there, and a lot of vendors don't necessarily pull in the code and the fixes from upstream, and they don't necessarily, they hear, oh, there's this PC attack, maybe it doesn't affect me, right? I'm a Mac. So beyond this, there's problems such as Intel has recommendations about protection mechanisms that vendors should use, and not all the vendors use those. Beyond that, there's still these decades of legacy decisions and things like option ROMs, which Trem will talk about later, which lead to sort of inherent built-in vulnerabilities. So we considered a bunch of different vulnerabilities. We took a bunch of old work and we said, do these apply to Mac? And so all of these should be old news at this point, right? These are all things which were responsibly disclosed over the last couple of years, publicly disclosed at conferences, and yet when we came along and we said, let's take a look at the Mac, are they still there? Yes, they are. Right? That's not cool. So the first thing to think about is the speed racer vulnerability. This is actually vulnerability in Intel hardware. So this is not the kind of thing which we would expect any given vendor to say I'm not vulnerable to, because if you're running chips, the core vulnerability is in Intel hardware, and the core fix is to use some Intel protection bits. But Speed Racer is going to be a race condition, a hardware race condition, and that we'll see why exactly that happens. So if you look at the BIOS control register on Intel hardware, this is sort of the oldest protection mechanism for the firmware. It says, okay, am I allowed to write to the BIOS? There's a BIOS write enable bit. That must be set before you're allowed to write to the BIOS. Now, if a vendor wants to stop any malicious OS attacker from writing into the BIOS, they need to set the BIOS lock enable bit. BIOS lock enable bit says, if someone sets the BIOS write enable bit, I want to cause a system management interrupt. I want this code that I've put into SMM, system management mode, I want to catch anyone trying to set the BIOS write enable, and I want to probably stop them from writing into the BIOS. So that's the oldest, most common functionality. But what the Speed Racer vulnerability disclosed is there's this hardware race condition where once we have multi-threaded hardware, right? So back in the day, that was just single-threaded hardware, single-core hardware, and so that protection mechanism worked great. Once you have multi-threaded, multi-core, hyper-threaded type hardware, you can have an attacker who just continuously hammers on the write enable bit. They say set it writable, set it writable, set it writable. And then in a separate thread, in a separate core, they continuously say write this value to the BIOS, write this value to the BIOS, write this value to the BIOS. And so the core race condition is those two threads continuously are just hammering on trying to write to the BIOS, and eventually we found that they're always able to succeed. This is the kind of race condition which an attacker likes, right? There's no penalty for failure, and beyond that, you just keep doing it long enough and you're always guaranteed to win. So, Corey talked about this back at CCC in December 2014. This was disclosed privately to Intel and CERT in May of 2014, and so this has been out there for quite a while. So Intel's sort of response to this was, okay, well, we recognize that that could potentially be a problem, but we'd already added this new protection bit back in 2004 to our newer platform controller hubs, and this new bit says, even if the BIOS write enable is equal to 1 somehow, I still want to stop an attacker from writing into the BIOS unless they've broken their way into system management mode. So this bit says you must be in SMM before I allow you write to the BIOS. So that requires an extra exploit, an extra bit of effort on behalf of the attacker. They can't just race from kernel space and set and write to the BIOS. So this is basically the way that Intel says it should be. This is the way Intel recommends that BIOS vendors actually set their protection bits. So you've got layers of protection, each of which provides some architectural value. So the BIOS lock enable says system management mode, they get to man the middle every attempt to write to the BIOS, and that will be stopped and checked. Well, that's the problem. The problem with that is Speed Racer bypasses that. But if a vendor sets SMM BWP, then that will also say you must currently be in SMM before I'm going to let you write to the BIOS. And beyond that, there's further protection mechanism called protected range registers, and these allow the BIOS maker to set non-contiguous slices of the firmware as non-writable. And typically, a firmware maker would set the code as non-writable even from SMM. They basically say lock it down, and this is the kind of thing where it would be locked down, and you want that to be stopping an attacker in SMM from writing into the flash chip. So when we go back and we said, okay, let's consider this, let's see whether or not this is Apple's vulnerable. First thing is we check the CERT vulnerability disclosures. So the really nice thing that we like about CERT vulnerability disclosures, the reason why we used CERT for our coordination even when we were at MITRE and even when we had CVEs available to us, is that CVE just tells you these vendors are vulnerable and they've said they're vulnerable. The CERT ones are nice because CERT handles the coordination for you, and then they go around and ask the different vendors, are you vulnerable? And they get back responses. So there's going to be some vendors that say they're vulnerable, and then usually there'll be a link to their fix on the CERT disclosure. And then there's some vendors that say we're not vulnerable, and then there's vendors that don't say anything at all, and you can probably guess that they're going to be vulnerable. If they don't even care enough about firmware security to respond to vulnerability disclosures, they're probably going to be vulnerable. So we looked at Apple. Apple said it's not affected. Okay, well, this is a fundamental hardware race condition. All the Intel CPUs have this, so that bears investigation. And like I said, if vendors don't actually respond to these, and if you don't hold them accountable, if you don't say, hey, I saw this talk about whatever, are you actually vulnerable? They just aren't even going to say anything. So we need to check Apple. We need to say, is Apple vulnerable to this problem? So you go in, you look at the BIOS control register. The BIOS control register is set to 8. I won't make you do the bit math in your head for that. But the basic result is BIOS lock enable, not set. SMMBWP, not set. Right? So they're basically not using those first two layers of protections. So in a very technically accurate, pedantic sense of the word, Apple is not vulnerable to Speed Racer because you don't need to use an exploit to get around protections that just aren't there. So this is what protection looks like on a new Mac system. I went out and bought the absolute newest Mac Mini, and this is the protections I saw. So you see, they're not even using the first two protection mechanisms, so that means they've got a single point of failure. Right? And beyond that, there are gaps. There are gaps in this region. The first gap points at the EFI variables. If you use the command line tool NVRAM, you can twiddle NV variable bits. But even some variables are prevented from being accessed by NVRAM. But if an attacker knows how to write to the flash chip, they can just bypass whatever Apple's API is to writing to the variables, write directly to the flash chip, and modify any variables that they want. Beyond that, there's an additional sort of gap in this protection, which we don't even know what that does, right? But as testing this sort of attack, we go ahead and we say, all right, corrupt that, write all X's into that, and let's see what happens. Well, what happens is the system is bricked. It will never ever boot again. Right? And that's undesirable behavior. So there's a video for that online which you can watch, but it's kind of hard to show, a cool demo video. Look, the system does not boot. It's just a picture of the system. So we decided to skip that, and you can watch that video online if you'd like. So, second thing we need to look at, Darth Venomous vulnerability. I've got a goon crawling up here. I don't know what he's doing, but okay. So, Darth Venomous vulnerability, right? So we saw that the protection mechanisms still have the protected range registers. Attacker would like to get around that, modify the code and stuff. And so that's exactly what the Darth Venomous vulnerability allows an attacker to do. Sometimes called the Dark Jedi attack, this was named by Rafal Wojcik because basically Darth Plagueis defeated Darth Venomous, killed him, put him into this, and then continued to resurrect him, and then kill him and resurrect him and kill him and resurrect him. I'm not, I don't know the exact story, and consequently it's been said that this is just like, maybe he didn't kill him, he put him into a coma, that sort of thing. But the analogy here is that we want to continuously kill and resurrect the system and use it to study the system, find vulnerabilities for science. So the Darth Venomous vulnerability is the situation that when you put your system to sleep, just normal sleep, not a hibernate, not a, what does Apple call it, deep sleep. If you just put the system to sleep, close the lid, you're going into what's called ACPI S3 sleep. This is a low power mode where the hardware tries to power off as much of the motherboard as it can. Well, some of the stuff that it powers off is parts of the chipset which allow these protected bits to become unset, right? You're going into low power, you lose all of your electricity and the bits get unset, right? And so this can be manipulated by an attacker. So this vulnerability was disclosed to CERT and the newly formed UEFI security response team back in September of 2014. And then this was publicly disclosed in December of 2014, as Trammell said, day before his talk, and wanted to find out whether this applies to Apple. So very, very quick, I recommend you go watch the actual talk if you want to know the details, but at the highest level, the details of Darth Venomous are this. A normal system, when it's booting, is going to take that top path there. The normal boot path, you're going to execute each of your EFI or UEFI phases. As the system's booting, it's going to save information about which hardware configuration bits it's set to this little cheat sheet. This is boot script, this S3 boot script, which is going to be stored in RAM somewhere. Well, unfortunately, it's stored in unprotected RAM. That's the core of the vulnerability. But when you go into sleep and you wake back up, the resume execution path is going to say, instead of executing all of my normal boot code, which would make my resume from sleep as slow as a normal boot, I just want to consult the cheat sheet, and it will say, it has these type of operations. You can write to I/O, you can write to memory. And so you basically just go down the line and interpret this boot script and that will make it so that the hardware will be reconfigured the same way it would be with a full boot, but much, much faster, right? That's why you have the nice, quick wake from sleep. But there's a core problem with this boot script, core vulnerability. The vulnerabilities are twofold. One, the script gets stored in non-protected RAM. And why does it get stored in non-protected RAM? Well, because you look at the spec document from 2004 and you can see right there, they're recommending storing it into this ACPI non-volatile memory. Well, the thing is that memory is just memory like any other memory. An attacker can manipulate it, compromise it. When they go to manipulate it, there's this one sort of catch-all opcode. There's this dispatch opcode. And the dispatch opcode says, whatever I need to do to configure hardware, it's too complicated for just, combination of reads and writes, things like that. So instead, I'm going to jump off and I'm going to jump to some arbitrary code that's pointed to by the dispatch opcode. So a script that has jumps to arbitrary code plus an unprotected script somewhere in RAM means that attacker can compromise the script, get rid of the protected range registers, and have access to everything. Get access to the code, modify the code so that right from the very beginning, all of the code is compromised by the attacker. So that's the net result of the Darth Von attack. So when we go back and we say, did Apple say they were vulnerable or not vulnerable, look at the cert disclosure. In this case, this particular disclosure, unlike all of our past ones, was a little weird in that we saw CERT had been listing only the affected vendors, only those vendors that replied and said they were affected. So at first we didn't know, did Apple say they were not vulnerable? Did CERT not actually contact them? But by running it to ground, we found out that CERT hadn't actually contacted them and told them about it. Well, that's fine, but it was still also coordinated through the newly formed UEFI security response team. And since Apple is a UEFI board member, you would expect them to listen to the UEFI security response team, right? So, again, the big finding from Darth Von is the fact that previously Trammell's attack was the first thing that showed and proved that you could write Apple firmware. There had been, Snare's earlier 2012 attack, there had been some thought that maybe Apple firmware was somehow protected by extra hardware, something like that. Trammell showed, no, that's not the case. You just need to know how to fix up CRCs and things like that. And once you do that, you can write to it. But again, ThunderStrike 1 required physical access with the the Thunderbolt device itself. So Darth Von says, no more physical access is required. Anyone who can get remote access to the system can manipulate that script in memory and then make it so that when you go to sleep and wake it back up, you can compromise it. Now, sorry that this is so small that no one who didn't sit right up next to the projectors is going to be able to see that. But this is showing, just a plain Jane software attack version of this. So once you've used a root privilege exploit, you can look and inspect the system, right? Inspect the system. It does have protected range registers. They are protecting the code. But then you find the boot script in memory, you find one of these dispatch opcodes, and you point it at some other address where you're going to put code. So point it at a different address, insert code into that address. And so the specific code we did here was to set a lock early. So basically the boot script's going down, 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 and it's interpreting stuff. The protected range registers get set somewhere lower in the boot script. Somewhere higher, there's going to be this dispatch opcode. And so all we do is we just lock down the registers and say no one is allowed to modify these protected range registers. In so doing, they get locked into a default 0 value that they had when they got cleared because you lost power. Right, so when we do that, then you set it to sleep, then you wake it back up. There you go. After wake, now the protected range register is all 0, locked in, can't be changed until the next, sleep resume cycle. So after that, right, we've just taken out protected range registers. Apple doesn't use BIOS lock enable or SMMBWP. That means, go to win. The attacker can write anything into the firmware. And here we just showed writing hello world into the firmware someplace we knew wouldn't actually brick the system. So another vulnerability very similar to this that you may have heard of a couple months ago is called Prince harming. So we'd actually seen this vulnerability in the past in other vendors, called it Snorlax, and told CERT about it back in 2013. Unfortunately, the vendors fixed it before we told CERT, you can make this live now, it's been, fixed. And then CERT said, well, it's been fixed, we don't need to coordinate this anymore. So they kind of wouldn't post our thing for a long time until Pedro Valaca came along this past May, and he found the exact same sort of vulnerability on Apple's. Right? So Pedro came, found the same vulnerability. We said, dear CERT, you can start coordinating this now. It's open 0 day again. So Pedro didn't give it a name, but he didn't want to go the hype route. But Katie Moe suggested Prince Harming because this poisoned kiss wakes you from sleep. So we're going to go with that. So his blog post said basically he had seen the title for this talk. He saw ThunderStrike 2 Sith Strike, right? And he correctly caught the implication of that. Sith Strike probably has something to do with Darth Venomous, right? We're probably saying ThunderStrike, Mac stuff, Sith, Darth Venomous, right? So he said he had been looking into the Darth Venomous attack on Macs, and he had been, using some other proof of concept code that was put out there by another researcher to look into it. When he looked into it, what he found was this Prince Harming vulnerability, which at the end of the day was actually a little more severe than Darth Venomous because you didn't have to do anything special as an attacker. You just put the system to sleep, you woke it back up, and everything was unprotected. They were just not even setting any of the protection bits that mattered on resume. So this, he was a little concerned about this as a Mac user. I was a little concerned about that as a Mac user. It leaves something to be desired when an attacker can just sleep your machine, wake it back up, and write into your firmware. That's not good, right? So we had not actually reported the Prince Harming vulnerability to Apple. Why not? Because we were testing on our MacBook Pro 11.2s, which turned out to not actually have the vulnerability. So Prince Harming was actually fixed at some point. His 10.1 had it, our 11.2 didn't have it. So Apple basically silently fixed this at some point, and they didn't backport it to older machines. So consequently, what that meant was, accidentally this blog post went live. He thought that we had told Apple about it. He thought that Apple would already know about it because of disclosure of Darth Venomous. But nope, Apple didn't know about it, so oops, Apple is 0 day. Now anyone can break into the firmware, right? But the core question is, why are there 0 days just laying around to be found like this on Apple? That doesn't make me happy as a Mac user. I'm sure that doesn't make you happy. So now that there was a full disclosure vulnerability out there in the wild, right, Apple turned around a patch relatively quickly. So basically, they put out this EFI security update 2015-01. It affected, they patched 24 different models, and the models which they patched were basically everything from 2011 and newer. So if you have a system from 2011 or newer, right, hopefully you're just applying Apple's updates as you go. But how did they actually fix this, right? So they fixed this with improved locking. And so the question is, what does that exactly mean?
So I was very curious, what is this improved lock-in? So I did a binary diff and dug into their update. And what I found is that they've moved the protected range register and flash lockdown configuration register setting out of the boot script, and they lock it in PEI before they begin executing it. And this is the right place to do it because you don't want the protected range registers ever unset. So this does prevent the demo that we showed from being able to write directly to the boot flash. However, they're still not using the BIOS control bits, so it's still possible to brick the system. The S3 boot script is still unprotected, so you can do all kinds of interesting stuff in PEI long before lots of other protection is enabled. There's also some obscure features like TSEG-MB that were discussed in the original Darth Venomous attack that are left unlocked, which means that it's possible to DMA into SMRAM, which can then get code execution in system management mode. And something that I find very worrying is that the brand new MacBook, the USB-C only one, is protecting the boot script in some way. So this means that there are now two classes of machines, some which are vulnerable to Darth Venomous and some which are not. So the fourth vulnerability that we take advantage of is a really legacy feature of option ROMs. And this goes back to the original IBM PC with the 8080. The BIOSes in that era were typically socketed ROM chips. And there's also empty sockets on the motherboard for optional expansion features. This is where you could put your basic interpreter or your hard drive controller. The ISA expansion bus also allowed cards to contain option ROMs. So this allowed you to drop a new video card into your system and have the BIOS be able to display onto it. Unfortunately, because this gives you code execution early in the boot process, it's a great place to put malicious code. And this is not a new idea. John Heisman presented it at Black Hat in 2007 with a modified PCI, at that time PCI card. And then in 2012, Snare gave a amazing talk at Black Hat showing how to build EFI rootkits that ran out of the Thunderbolt Ethernet option ROMs. And his talk is what actually started my research into MacBook security. Intel realized that this was a problem for any sort of trustworthy boot. So as part of Secure Boot, they required that all expansion card ROMs be signed, cryptographically signed, with a key stored, with a public key stored in the boot flash on the motherboard. And they required this for Secure Boot in UEFI 2.3. As we've mentioned, Apple has sort of frozen on EFI 1.10, which doesn't support the secure boot concepts, and they still unconditionally load and execute option ROMs from both internal and external devices, like the Thunderbolt. This is despite Heisman's talk in 2007, this is despite Snare's demo in 2012, and despite my ThunderStrike demo in 2014. And what it really needs is an architectural fix. Either security-conscious users need to be able to disable loading of option ROMs, or whitelist hashes of option ROMs, or signatures on option ROMs. There are quite a few steps that could be done here. In the ThunderStrike talk, I hypothesized that the option ROMs could also be used to spread malware virally. And this is an improvement over John Heisman's talk that had the option ROMs on PCIe cards fixed in systems. But now with Thunderbolt, devices can be shared between machines. At the time of my talk, it was mostly a hypothetical, because to rewrite the option ROMs required booting to DOS and plugging in the adapter. But what we realized is that the Linux kernel Broadcom 57 device driver had all of the hooks for reading and writing the option ROMs. So we were able to port that over to OS X, and now it's possible to install new option ROMs into these removable devices with just root access. We also ported it to run in the DXE environment, so that it's possible for ThunderStrike to rewrite from the option from the boot ROM. So the way that this could be used maliciously is that you get a remote shell somehow, use whatever exploit of the week, you install this whitelisted driver, and then you're able to flash code into the Thunderbolt device. And we use the Thunderbolt device because they're very easy and very small and cheap, but lots of other devices have option ROMs. A lot of Wi-Fi cards do. A lot of GPUs do. A lot of SATA controllers built into SSDs have them as well.
Right, so again, back to the main point of the talk, right? UEFI vulnerabilities shared across many systems, right? It's highly likely that any given vulnerability that's found is going to port to everywhere. So ultimately, in this work, we considered 6 vulnerabilities that were all old, all publicly disclosed, all privately disclosed. And we said, which of these affect the Macs, right? So there was Prince harming, which was patched in the June 2015 patch by Apple, completely gone now. That's not an issue. As we said, Darth Venomous is only partially patched. You can still use it to break into SMM, which is not good. We've got Speed Racer, which we're still vulnerable because Apple doesn't use SMM BWP, so we don't have to get around that vulnerability. But then the really interesting thing is Queen's Gambit. So Queen's Gambit, we presented here 1 year ago at DEF CON. Corey just won a pony for it the other day because it affected hundreds of models of PCs. But a vulnerability that had been disclosed privately 1.5 years ago, publicly 1 year ago, is still actually affecting Apple systems. They're not patched yet. Apple is working on a patch for them. But so although they patched the basic thing that would allow our current proof of concept ThunderStrike 2, this vulnerability could do exactly the same thing. So that's still out there and open. And then the Sicilian is a much lesser known vulnerability. This just had to do with us trying to make a point that previously Invisible Things Labs had said if you break into BIOS, that if you break into SMM, that does not imply you can break into BIOS, but if you break into BIOS, you can always break into SMM. We wanted to show that you can break into BIOS from SMM on some systems, just by way of saying, this is a possibility. The sixth thing that we considered was the setup vulnerabilities that are very common amongst UEFI systems. The setup variable will have configuration bits which will affect secure boot. Well, again, Apple doesn't have secure boot, so even if they had this variable, it wouldn't matter. But the setup vulnerability can be used to get bypass secure boot on a lot of PCs, and if you just corrupt the variable, you can brick the system. This vulnerability, though, does not affect Apple's whatsoever because they don't use this variable. They don't have an equivalent sort of variable. So 5 out of 6 old public vulnerabilities all affected Apple systems, right? That's not what we wanted to find, but that's what we found. So what can vendors do, right? We always go around and we help vendors understand, Intel's recommendations should really be thought of as requirements. They're not really recommendations. There's a reason why Intel said that you should set all of these protection bits. You don't want to have a single point of failure when you're only using one of them, right? So obviously vendors have to test all of these old vulnerabilities against their systems. All of those vendors go look at the cert disclosures, see whether you're currently running a machine that your vendor doesn't even respond to vulnerability disclosures, right? They're probably vulnerable. Obviously setting all the protection bits. ChipSec is Intel's tool that they had been privately passing around to BIOS makers in order to have them fix vulnerabilities before they ship. Right, and then they eventually made it public for researchers to play around with. Right? If you run ChipSec on an Apple system, well, it doesn't support Mac, unfortunately, so you have to either run it from EFI or install Windows. But if you run it, ChipSec would say this system is vulnerable. Right? If Apple were using ChipSec, they would understand this system is vulnerable. And then there's other things like the SMM lockbox, which can make it so that the S3 resume script is not just sitting around in RAM where anyone can manipulate it. You lock it back in system management mode where an attacker would have to have an extra exploit to break into SMM before they could manipulate it. Right? That's not a panacea, though, because even at the original Darth Phenomenus attack, they showed that some Intel systems were using SMM lockbox, but just because you hide your stuff away in RAM, if it still jumps out and reads from other unprotected memory, well, that's a bug as well, right? Intel BootGuard is a great technology that allows a system to actually have a much stronger root of trust so that instead of the very first instruction coming from your potentially manipulatable firmware, instead it comes from signed code where literally the CPU verifies the digital signature on that code. So that's a much stronger upfront guarantees. And then of course option ROMs, there's many things that need to happen for improving option ROM security. Digital signatures are a good first step, but that's not an end step. And certainly it would be nice to have the ability that if you're security conscious, you're setting a firmware password, something like that, maybe you wouldn't like all of these untrusted, unsigned code to just be sucked in and executed in the BIOS. All right, for all of you who are not BIOS engineers, who don't spend your day making BIOSes all the time, what can you do? Well, you have to start doing firmware forensics, right? It's not just about hard drives anymore. It's not just about RAM, memory forensics, right? You have to do firmware forensics. And as I said, people have been running around giving these sort of talks for years now, but no one ever seemed to do anything about it. No one ever seemed to actually, provide ability to check the firmware. And so that's sort of why we started LegBookCore. But in order to not leave you empty-handed here, we put out an option ROM checker, right? So you go, you plug in your Thunderbolt Ethernet adapter into your machine, plug it into your machine, and then run the scripts that we've provided. It will dump out the option ROM using the stuff that's been ported over from Linux, dump the option ROM, and then integrity check it, because it turns out everybody's option ROMs that we've seen, they all look the same, and they're very easy to integrity check. And so this gives you a first order, is there some manipulation of my option ROMs? So we've only checked it on our own and, a few devices beyond that. So if you go check yours and it says there's an error, either A, our tools are broken, highly possible, or B, you actually have some attack. So in either case, whether it's a false positive or true positive, we'd like to hear about it. The other thing you can do, I always have to put my plug in here, the other thing you could do is go get smart on firmware, right? Go learn x86 assembly, go learn about rootkits, go to open security training, take some free classes, get smart on things, and then go off and do your own firmware security research.
All right. Thanks so much for attending our talk this early Saturday morning.